La siguiente conferencia es Docsis 4. Le damos la bienvenida al doctor Alex Adams, SCTE, y también Managing Director en Adams Group. Bienvenido.
Exactly. Well, thank you very much. Let me get settled here for questions later. Buenos dias. Is it dias? Yes. Buenos dias. I'm Alex Adams. With a melodic name like that, you'd think I was American. I'm not, I'm German, but I have been Americanized, North Americanized, 12 years of my life. So I come over as a hybrid. Unfortunately, I do not speak much Spanish, none at all. So please bear with me. A little word on myself. Managing director of my own company, pretty much inherited from my dad, who founded it. I'm a professor for electrical engineering in University in Northern Germany, where I actually have Germany's own master program for broadband engineering that I teach, so I can make my own engineers, which is an edge my company has. And for the past 8 years, I've been working for SCTE, creating content and also teaching it worldwide, amongst others, for Cablevisión here in Argentina a few years ago, which is always one of my favorite destinations. So I'm the SCTE's egghead, somebody who is a theoretician, who explains how technology works. Whenever it comes to hands-on, how do you splice a fiber and how do you actually do that, we got other people for that. So you're going to be getting, so to say, how does Docsis 4.0 work as a lecture. And I call it Pimp My Docsis into Symmetry. You know, it's a TV show in the United States, Pimp My Car, make a rusty car into something shiny again. And we're going to make something old new again, a good new version of Docsis. So let's see how this works. Let's do some Docsis. Hey, it doesn't work. Now it does. So the past few years, talking the past 7, 8 years, have seen some significant technical developments in broadband communications. We as an industry, we have the advantage of having our own laboratory, an international laboratory. It's not just an American one, it's the Cable Labs. And the Cable Labs research the technology that we're going to be using in the next years, how we're going to be keeping our edge in comparison to our competition. And it's the SCTE, amongst other things like teaching, that takes this research and pours it into a standard, brings it through the committees to make it an official standard. So it's also part of our work. And Docsis 3.1 and distributed access architecture, like remote PHY systems, remote MAC PHY systems, are good examples for technologies of those last years that kept our edge, that pushed the fiber closer to the customers, reduced cluster sizes, and enabled us to deliver gigabit services to our customers. We can actually now say, well, you can get a gig downstream, right, with Docsis 3.1. So Docsis 3.1 enabled us to get over our spectrum, not to the individual customer, but over the spectrum, 10 gigabits per second downstream, 1 to 2 gigabits per second upstream. But the pandemic showed that's not enough. We need to go a step further. We also, in the past years, replaced our analog lasers, our analog optical fiber links, into digital ones, which basically makes an Ethernet link between our CMTS and our optical nodes. We smeared out the functions of our CMTS into our optical nodes, which has a bunch of advantages. So our Ethernet is already at the optical node, and at one point it's going to go into the modem. But we're not there yet. But we are going to, with every upgrade, we push our nodes deeper into the network, as you guys know. And all the customers, small optical node sizes, just a few customers on it compared to the 1,000 that we used to have, share this 10 gig Ethernet connection. And that is the path we want to continue, where the business case allows it in the future, and that's called Docsis 4.0. First of all, what is the driver of our industry? That's this guy here. Well, he's not really the driver, but he is Jacob Nielsen. And the man's still alive. This is pretty much an actual picture of him. He's a Danish engineer who, like 20 years ago, did the observation that the customer demand in bandwidth, in data rate requirements, doubles about every 2 years, which puts us into the situation as an industry to every 2 years be able to deliver that extra speed. So we're constantly upgrading. After the upgrade is before the upgrade. After DOCSIS 3.1 is before DOCSIS 3.1. So we constantly feel the need for speed, right over here. Since we're in South America or in Latin America, that's the need for speed here, right? Arriba, arriba, andale. I grew up with this guy, yeah. So DOCSIS 4.0, a few opening remarks. The whole process of pushing the fiber closer to the home, the whole process of using our coax is not concluded. In the future, we're going to be continuing doing what we did, but we're just putting a technology edge onto it. I usually say every HFC network wants to be a pawn when it grows up, because that's what we're working for. At one point, we want to have our fiber into the customer's modem. The question is just, how are we getting there? And when are we getting there? Are we doing it right now, pull fiber? Or are we actually going to leverage the existing coaxial footprint? Now, fiber is so close to the customer already that it becomes a business case decision. It depends on the boundary conditions of your network, as you'll see. DOCSIS 4.0 does provide the symmetrical 10 gigabits per second in both directions. And you can do that, and you'll see it's a very powerful standard. You can do that with two different technological approaches, both covered by the standard. The network operator decides for one or the other way when he executes it. Existing networks, existing coax, has a wonderful advantage over a fiber optic network that I still have to put into the ground or hang on masts that I want to build to overbuild my coax. They're actually paid. The coax network, in most cases, is paid for, right? And therefore, it's yours to use, and you don't have very much investment. That's why we're using our coax. And we want to continue doing that where it's feasible. Of course, whenever in this industry we're going and we're upgrading, if you want to have an optimal solution, you can actually send a physicist, right? Because he will get you the optimal solution. It's going to be very, very expensive. Engineering is about pushing technology, pouring some research into technology, and then making it cheap enough to be mass-produced, to be a business case. So I summarize that as, I'd like this for the price of that. That's usually the boundary condition every upgrade goes by, right? But don't be mistaken, we are going to have fiber to the everywhere. We have fiber to the everywhere at this point. Our HFC networks are mostly fiber. It's just the last few hundred meters that is coax. Network operators in the United States, it looks like they're going to be deploying this DOCSIS 4.0 technology, either as we're going to go into the FDX option or the extended spectrum option. European operators have underground networks, like in Germany, direct buried underground networks, completely different scenario. So over in Europe, with underground networks, you got to do business cases for pretty much every network, every part of the network, because you have to do lots of civil work. Civil work is very expensive. But FTTX family, just for completion's sake, we're not going to go over it, but we have a whole bunch of FTTXs here over the past 20 years already, since we do HFC. The most important one is not fiber to the toilet, which is a nickname to fiber to wherever you want it. The most important one is fiber to the desk, because that means fiber into the modem, which means a complete full Ethernet connection between your CMTS and your modem, and that is a PON network. That's where we want to get at one point. Question is, how are we doing it and when are we doing it? As long as there is a single meter or inch or centimeter of coax between your optical node and your modem, you will have a need for DOCSIS or for GFast or for MoCA, some kind of protocol change that transmits signals on coax. So let's go into what is this DOCSIS 4.0. We heard a little bit from Gustavo, and I'm going to go into the details a little bit more. So symmetric DOCSIS, 10 gigabits per second in up and downstream. How are we doing this? First, some general remarks about DOCSIS 4.0. Why are we doing it? Because the market demands it. If you think about it, everybody wants gigabit service, but my household, 2 daughters, wife, me, I work a lot, everybody works a lot on the internet, 150 megabits per second is enough, right? But it's kind of like a sales kind of thing. Remember 20 years ago, everybody wanted to have a flat rate? I'm getting 1 bit per week, but I get as much of that as I want, right? So it's often these buzzwords push customers into a certain way of thinking, and that's a little bit what we're going on here as well. But we need to pull suit to be able to compete to with fiber to the home companies. In fiber, symmetry has been normal. Up and downstream symmetric throughput always has been this way. In coax, it has not been like that until now. And it's Docsis 4.0 that does this symmetrical throughput that introduces it. So we increase the lifetime, once again, of our coaxial plant near our customer. I always call it make it believe it's a fiber optic connection. Why? Because we got to compete with fiber operators, and our MSO, our network operator, in essence, only owes the customer a throughput, a data throughput. The customer really, in most cases, doesn't care how he gets his internet. Well, if you ask my daughter, my younger daughter, well, it's just there, right? So in Docsis and any kind of Docsis and distributed access architecture, all this engineering that we have been doing these past years is just time-buying projects for the network operator to drive his own fiber close to the customer, not because the competition pushes him now, but on his own accord over the next years. Much better business case that way. In the end, it's just all business. Docsis 4.0 consists of 3 parts. Consists of the part full duplex Docsis, which is frequency region that can be used in both directions at the same time. Second option is extended spectrum. Gustavo already elaborated on that a little bit. You basically do what we did all the time. You just take bigger blocks for upstream and for downstream. There's also the low latency Docsis in there. So basically 3 aspects to it. I'm going to go in detail on 1 and 2, not too much on 3. So basically, I always say this kind of resembles lobscouse. It's like a leftover food kind of thing. Why do I say that? Kind of, Navy ships. I come from the coastline in Germany. My father was in the Navy, was a naval officer. And when a Navy ship is out at sea for 3 months, the stores are running low, the water runs low, and then they kind of make food out of what's left over, kind of camouflage it with beetroot. Like that. Doesn't taste very well, but it fills up. So it's kind of leftover food, and that's what Docsis 4.0 is essentially. Because the extended spectrum to 1.8 gigahertz, that's already in the Docsis 3.1 standard, not as a must carry, but as a can carry. No network operator worldwide did this option. They all extended their downstream to 1.2, if they did that. Full duplex Docsis, is that 4.0? No, that was actually researched once they were done with Docsis 3.1. It's the Annex F of the Docsis 3.1 standard. It's not part of the Docsis 3.1 standard, but it's kind of got annexed, it got researched as they were doing that. Low latency. Well, that was kind of taken care of with Docsis 3.1 as well. Distributed access architecture, perfect example. When a modem and the CMTS communicate, MAC management messages back, forth to organize the logistics of a transport. The signals used to have to go from the modem all the way to the CMTS, which was maybe several kilometers. Now they just go to the optical nodes, which is a couple of hundred meters, maybe a few hundred meters. So that already reduces the latency of our signals a lot. So Docsis 4.0 offers these 2 different approaches. Larger chunks of the spectrum, as I said, or introduce a special, really beautiful region in your spectrum between 108 and 684 megahertz that allows signals to move in both directions at the same time, even on the same subcarrier, which is an engineering no-go, but we can work our way around that. Downstream frequency is extended to 1.8 gigahertz. The upstream to 684 megahertz. It does not mean that you actually have to use that, but to get the Docsis 4.0 specification stamp for the equipment, as is specified, that's working according to spec, this is a must carry in Docsis 4.0. FDX operational frequency band, if you're going FDX, is between 108 and 684 megahertz. If you're doing FDX, it needs to be in that region. And the Docsis 4.0 is designed upon an N+0 infrastructure. Optical node exchange the optical signal into an electrical signal, and then no more amplifications, ideally. It does work with extended spectrum with more amplifications afterwards. Even with full duplex Docsis, they are working on it right now to actually do N+1, N+2, but then the signals are noisier. So we're basically down to our trunk lines. Fiber to the last amplifier with Docsis 4.0. Then we just use the coaxial trunk lines. Not trunk lines, what am I saying? Trunk lines. So with FDX especially, we're getting new types of distortions into our signals. And we already have a whole bunch of distortions in there. So we need high computational power to make the system work, especially if we're going FDX. Benefit? Well, that's what we need, the 10 gigabit symmetric data throughput. Pictures speak 1,000 words. On the left-hand side, the legacy Docsis 3.1, right? Legacy, put in the field 5 years ago, already legacy. Welcome to cable. You got an upstream region, which gave you the option of 85 mid-split or 204 high-split systems, and we had a big downstream region. See if this laser works? No, it doesn't. But the 1.8 gigahertz nobody took. It was 1.2 that people, like network operators, if they extended the downstream at all, would go to. The FDX option, Docsis 4.0 over here, you see it's a different spectrum. You got an upstream, generic upstream, just upstream signals. You got a generic downstream, which seems to have shifted up here a little bit, just downstream signals. You can take them to 1.2, you can take them to 1.8. And in the middle, you got that red section, FDX. Signals go in both directions at the same time. That's a problematic region as far as engineering is concerned. It gets complicated. For the extended spectrum option, you don't have this FDX region. You're just using a big old upstream. Does not mean that you have to fill them all up with upstream. The equipment is specified to do this. On the left-hand side, 10 gigabits per second, downstream, 1 gigabit to 1 to 2 in the upstream. Hybrid infrastructure, lots of single carrier QAM, Docsis 3.0 channels still in these 3.1 systems, and some OFDM, and maybe some OFDMA. Over with Docsis 4.0, it's backwards compatible. It works with 3.0, but in this scenario, mostly going to have OFDM. Especially in the upper frequency regions, you're not going to place any single carrier QAMs. It's just going to be OFDM. Little question to my translators, how is my speed? Good? Good. I have a tendency to speak German and English as fast as you guys speak Spanish, which is going to make these guys explode. Right, I stole this idea from CommScope, as a matter of fact, on the last SCTE. They had a slide, something like this. I redid this because it was cute. How are we actually getting to this 10G if we're using our coaxial plant? Well, we're right over here on the green line. It's basically like a subway system, right? So I found that cute. We want to get over here to the 10G. That's our station that we want to get to. And we are somewhere on the green line here as a network operator, Docsis 3.1. Now, if I want to get to 10G, as a network operator, I have to make the decision. Do I want to go extended spectrum to get there, or do I want to take the FDX route down here? That's a decision you got to make. In the end, once you're done, hopefully systems can converge as we're going to the next version of Docsis, but we'll see. If you're going the blue route, you're going the blue route, it's good to upgrade to 1.2 gigahertz. And use a high-split system, as a matter of fact. 1.2 gigahertz downstream, 204 megahertz upstream. That is already Docsis 3.1. That's the highest possibility of extending your spectrum in 3.1. Well, that's what people did in the upstream. If you go into the extended spectrum line, you see you're going to put in a 1.8 gigahertz downstream. Equipment is capable of doing that. You don't have to fill them all up. And then you gradually go and increase your upstream capacity. Right? You go 204, and every OFDMA channel is a maximum of 96 megahertz wide. So you add one more channel after another as you need that upstream capacity. So this is a tiered approach. In the end, both paths will lead to your 10G desired destination. On the bottom, you're going to have FDX. You should probably start with a mid-split system there. That's why you're branching off in the middle of your green line here. And you see the downstream stays at 1.2 gigahertz. Why? Why is that an advantage? Well, it's more complicated FDX-wise. That region is more complicated. But with the Docsis 3.1 upgrade, we exchanged a lot of taps, especially in aerial networks. So with FDX, that reduces that eliminates the need to go again and now upgrade your network to 1.8 gigahertz taps. We're going to get into that. And in the end, once we're back here, the next step could be a converging system, like a 4.0, 4.1, Docsis 4.1, Docsis 5, something like that, that has a 1.8 gigahertz downstream with an FDX region. Right? So that would be maybe the next step of Docsis. In the end, both paths will lead where you want to go. An Argentinian analogy, it does not matter if you're taking the Paris line or the Barcelona line. In the end, you're going to get to Argentina, right? Messi always pulls. That's good. He's the greatest player, one of the best to ever play that game. So let's go into the frequency division duplex extended spectrum Docsis. It's a long name, isn't it? So let's go into what that means. Frequency division duplex just means, well, we have data throughput in both directions, duplex, symmetric in this case, achieved by dividing the spectrum into an upstream and a downstream region. Does that sound familiar to you? That's what we've been doing all this time. Extended spectrum just means, no, we extend the upstream region, and we extend the downstream region into regions that we didn't use before. That's going to be causing some problems, but we'll handle. Basis is, all these Docsis 4.0 technologies work on the OFDM technology that was devised in 3.1. Subcarriers, cyclic prefixes, modulation orders, LDPC, FFT sizes, everything the same, 25, 50 kilohertz carriers, everything as we know it from Docsis 3.1. And this, the FDD, ESD, I'm just going to call it FDD or extended spectrum, these are one of the two from here on, expands downstream to maximum of 1.8 gigahertz, and that's what you will have to do to get that capacity, and you will also have to extend your upstream to 684 eventually. But it's called the business as usual, the bow approach to enabling 10G. It's what we've been doing. It's kind of your face sounds familiar kind of approach, right? We're doing what we are used to. Our prior spectrum expansions in the last years, they were primarily focused on increasing our downstream capacity. Currently now, even before the pandemic, the focus was on increasing the upstream, because there was already a whole bunch of home officing going on. Now the pandemic hit. I don't know how it was here, but in Germany, within a week, all the upstreams were clogged, because everybody was sending pictures from their home office, their living room, their kitchen, into the upstream, right? Well, we're all working from home. So that was a lot of work for our industry in the pandemic. Why do I want to do this business as usual approach? Because our troubleshooting techniques, our network operation techniques, everything that we have organized to run our networks these days don't really need much change if we're using this approach. Our techies, for example, they just have to deal with a bigger spectrum, but everything else is kind of the same knowledge base that they have. The training that you have to put into your engineers and your technicians with extended spectrum is a lot less than you have to introduce when you're taking full duplex Docsis. Also, with any kind of approach here, we're driving the nodes deeper into the network. The cluster sizes are reduced. And once we're down to Docsis 4.0, ideally we want to have 50, node size of 50, something like that. Combined with the expanded spectrum allocations, there is different options of how we can extend. You don't have to go you don't have to go to 684 from the get-go. You can do a tiered approach, as Gustavo already showed in his presentation, to roll out the spectrum. And then you can manage capacity from incremental capacity upgrades, like a simple little node split, to basically the management of upgrading your entire network with this kind of approach. It's very efficient, and it lets you upgrade your network where upgrade is needed and where you can actually make a little revenue on this extra bandwidth that you're supplying there. You know this picture here? Gustavo actually made this picture new. I got it from a research paper. I just stole it. And it's actually paper by Comcast and by Charter. We're starting with a high-split system on the top, right? That's a high-split Docsis 3.1 system. And you see, as we're upgrading now and we're expanding our spectrum, where we're using more than 1 gig, we're going to potentially 1.8 gig with only OFDM. We keep anything below 1 gig as our potentially single carrier QAM, maybe a little OFDM in there, some legacy systems, maybe even some, I don't know, not high density, single density TV programs or something like that. It depends on the network operator and what he's delivering, what the status of his deliverance is. But you see, it's a phased approach. You roll out more and more upstream OFDMA channels, and that pushes out this downstream region. And the gap, the transition band in between, will increase as you're going up in frequency, because we usually say 20% of our upstream bandwidth we use as a guard band, we use as a transition band. It has to do with the fact that you're filtering a bigger region, your flanks are going to react a little different. You need more space. So this transition band is there for filtering with a diplex filter. Extended spectrum DOCSIS uses diplex filters, just all the same as we're used to. The splits, I just put this in here to introduce that UHS is the ultra-high split. You see that this gap gets bigger and bigger. I don't want to be riding on this. This is always 20% of our upstream frequency. There's always a question, I leave 100 megahertz in my spectrum free there. Why do I have to leave so much? I need it for filtering. Because frequency is what the network operator banks on. That's what he sells. The more frequency he's got, the more content he's got, the more he can actually deliver to his customers that the customers will pay money for. My own little drawing here, another extended spectrum extension example, now starting with a typical North American or European system. This is a North American one, 42 megahertz upstreams, legacy upstreams. You got your downstream region as we know it. You got a little bit of usually one OFDM channel somewhere over in the roll-off. That's what lots of network operators did. And now I want to upgrade that. The first step would probably be to just go to a high-split system. That's not DOCSIS 4.0 at all. That's DOCSIS 3.1. And then go into the extended spectrum. Do I have to go all the way up to 684 megahertz? No. Here, my example, I introduced an OFDMA upstream from 5 to 396 megahertz. Because that is enough for the purpose right now, and I can push it out as I need it in the parts of my footprint where I can actually apply this. And you got your regions for DOCSIS 3.0 here for your old legacy systems, and down here in my extended spectrum example, I put a region in there for legacy DOCSIS 3.1. It's not DOCSIS 4.0 modems, but 3.1. You got to give them their little own little region, and you use OFDM down here. Or not down here, up here, in the extended spectrum part. So points to consider in this extended spectrum business. Active and passive broadband equipment is designed to work according to spec, to a specified frequency range. If you got a 450 megahertz plant, your amplifiers will have to amplify until 450 megahertz. Beyond that, it's not part of the spec. It's not going to work reliably. Same holds for passives. Passives are currently 1.2 gigahertz, specified max, right? Or they're less, especially if you got underground networks, like in Germany. Direct buried taps, we still have some 300 megahertz taps somewhere in there. So try to transmit a 1.5 gigahertz signal over a tap that is designed to do that until 300 megahertz. That's not going to work. You're not going to get a satisfactory response of the equipment. So passives need to be exchanged, no matter what you're doing, but there's no hurry since we're not going to go from 750 to 1.8 gigahertz. So as we're tiering our approach in rollout, we can go and exchange our taps. We have a little time for that. It's not a forklift upgrade. Actives need to be replaced to support larger upstream and downstream spectrum. As I just said, the amplifier needs to know up to which point he's supposed to amplify. And it gives you the tiered upgrade strategy, step by step, when and where it is needed. So this is a pretty powerful standard. It gets us our 10 gigabits per second, and we can actually apply it, well, wherever it's needed. This is actually an old slide. This is from the upgrade in Germany when we were actually doing bidirectional networks in 2001, and we unearthed a bunch of these old 300 megahertz taps that were in the earth for then 25 years already. And you see, this is a 20 dB tap. It looks in Germany underground, they look like this. So it's one tap on it, has 20 dB. Attenuation, and you see it's 20 dB down until 300 megahertz. And even after 25 years in the earth, they kind of still work somewhat reliably up to 300 megahertz. And as you go out, that's the frequency region, that's the design region. This is the out of design region. As you go out of that, it is completely unpredictable how this thing is going to act. I tried to put a distribution function over this data 20 years ago because I was good at stochastics at that point. As I came out of my master's degree, nothing fits. There's no known distribution that will actually describe this. So This, you can just say the further you go out of spec, the more likely it is that you're not going to have the attenuation that you're supposed to have. But is it going to be lower? Is it going to be higher? Nobody knows. So hard to be running a network on old equipment like that. So you want to update your passives when you're doing DOCSIS 4.0. Another question is total composite power. Nothing comes from nothing. So adding spectrum means transmitting more power. Power is energy per second. So you got more spectrum, you got to transmit more energy per unit time, especially in the upper part of the spectrum that you're extending. On the top here, this is the attenuation of a coax cable. You see it's not straight, it's kind of a square root of the frequency of your abscissa, of your x-axis here. It kind of goes like that. Every cable is a low pass. It's not a low pass filter, but it's a low pass. It means it attenuates lower frequencies less than it attenuates higher frequencies. And that's why we put a tilt in as we're sending our signals. More level, where it gets attenuated higher, less level, where it gets attenuated less, such that when it arrives at its destination, it's somewhat flat. So maintaining a realistic TCP while you're extending your spectrum all the way up to 1 gig requires actually thinking about tilt and output levels, and that's not necessarily trivial. And you got to work closely with silicon vendors here and basically do a lot of experience exchange, understand trade-offs between levels and performance. It's not enough to have an egghead like me talk about it. You actually need people with experience who've done this before on that job. One of the possibilities that you not could, but that you're solving this with is introducing a step in your amplification. You see, as 1.2, you only have OFDM. OFDM is very robust. If you reduce the transmission power just a little bit, such that you don't lose the efficiency of your OFDM, you will save a lot of power this way. And that's an approach that they're taking in extended spectrum. So, cool technology, huh? Kind of what we did beforehand, just a little bit put on steroids. So, but speaking of steroids, full duplex DOCSIS here. Now that's DOCSIS on steroids. We're going to go into how this functions. The other way, right? One was extended spectrum, was the blue line. Now we're going the red line. FDX, as I said, is originally not a new DOCSIS 4.0 related standard. It's the NXF of the DOCSIS 3.1. It's not part of DOCSIS 3.1. It's not a must carry, but as they researched it, I was like, let's research this as well. How do we do this symmetrically? It's backwards compatible DOCSIS 3.1 guaranteed, and 3.0 as well. If you have special, you got to introduce a special region there, especially if you're going to introduce a special region in your spectrum where you're actually keeping those legacy channels. But with DOCSIS 4.0, you're most probably not going to have much single carrier QAMs anymore. Yes. So this is the spectrum down here. And you see it has this red one in there. It's red on purpose because it's complicated, but it's cool. It's the coolest thing since sliced bread. This FDX part uses, this part of the spectrum is used for transmission in both directions at the same time. But you don't have to go and extend your downstream to 1.8 gigahertz. With DOCSIS 3.1, we extended to 1.2, some of us, network operators, and that's what you can keep. You don't have to exchange your passives when you're doing FDX. Comcast in the United States, network operator Comcast is going FDX. The other two big ones, Charter and Cox, are going extended spectrum. So it's a decision you got to make before you go. Yeah, so this is the cutting edge of technology, introduced in October 2017. Full duplex DOCSIS fundamentals here. Full duplex DOCSIS is based on an N+0 architecture. Ideally, the design is based on that, which means no amplification of the electrical signal after the remote PHY node. Well, it's just trunk lines. N+X is possible with FDX and currently being researched. However, the system is going to be noisier, potentially noisier, when you're adding extra amplification. So you're going to see why that is, because we're not using filters, because we're using directional couplers with FDX. If you have a frequency region that you use for both directions, it's impossible to filter one direction out as you do an extended spectrum. The big chunk of upstream, you can filter that, and suppress the downstream, or the other way around. You cannot do that in this FDX region. You can do it for the upstream. You can filter the upstream out, you can filter the FDX region out, or you can filter the downstream region out. That's why you have those transition bands in there. But in the FDX region, where it goes both directions, you cannot filter upstream and downstream. You got to use directional couplers. And a directional coupler is a little bit like a tap. Tap is also a directional coupler. And you know, they are not perfect. Power goes in directions it's not supposed to go there. The exit of a tap, or two exits of a tap, they are just decoupled with a certain attenuation. It's not blocked out. So power is bleeding in directions it's not supposed to go to. And that's the problem in this FDX region. Hold on. So, another thing is that a Docsis 4.0 cable modem either receives data or it sends data. It does not do both at the same time, contrary to all previous Docsis versions, including Docsis 3.1. Docsis 3.1 and everything earlier could actually receive downstreams on one frequency and at the same time send an upstream on an upstream frequency, because they are separated. In FDX, it is more complicated. It is either send or receive. And you're going to get a lot of trash signals in there. So CMTS takes a lot of calculation to clean up the signal. We're going to get into that, how that works. Specified a region for FDX, as I mentioned before, 108 megahertz to 684 megahertz. The start of the band is above existing mid-split systems, so above 85 megahertz. And the band must support, that's a must carry of the standard FDX is 3 OFDM channels of maximally 192 megahertz in the downstream. And the upstream, it needs to support 7 OFDMA channels in that 5 megahertz to 684 megahertz region that with FDX is you could use as your upstream. So it's like taking the guardrail out of a highway. So all of a sudden, it's not going one direction on one side and the other direction on the other side. They're basically going on both lanes in both directions. So in FDX, there's no clear separation between upstream and downstream spectrum anymore. In that FDX region, they exist in the same channel. That is important to conceptualize. Cable modem can receive data and transmit as scheduled by the CMTS, but you usually think, isn't that slower? Isn't that going to make it slower if it cannot send and transmit and receive at the same time? No, because if you switch fast enough between up and downstream transmissions, then it's actually faster than our existing systems. And it's all managed by the CMTS. CMTS is the big boss of our systems, as usual, right? CMTS is the multitasker. I always compare it with my wife. She can multitask. I'm more like a modem. I do what I'm told. Service groups get smaller with FDX also. M+0 environment, 50 households on a service group. And net result, of course, then 10 gigabits per second in both directions. And again, here are granular tiered deployment options. Just because you've got that region defined between 108 and 684 megahertz, it does not mean that you got to pack it full of full duplex Docsis channels. You can start out with a little bit, between 108 and 204 there, because that's the region you just need for the data throughput you got to deliver to your customers as this grows. Every 2 years, double the throughput. You can deploy more upstream and downstream channels, FDX-capable downstream channels, in this region between 108 and 684 megahertz. So far, so good. Where lies the problem? The problem lies with the interference. And that's where it gets a little bit more complicated. Because if you're going on the same frequency at the same time in both directions, that's an engineering no-go, electrical engineering no-go. We are modulating signals, different information on different modulation carriers, such that we are able to transmit these in parallel at the same time without them interfering. Now we're doing it on the same frequency. That's a little bit like a broken shielding in a coax, right? You got your transmission frequency and something radiates on that same frequency into your broken shield and overlays your signals. That's going to corrupt and destroy your signal. So that's why it's, oh my God. So why are we moving away from our basic principles here? Because we can. Because we know the interferences are going to come up, and we know how to counteract them. A single modem won't receive and transmit at the same time, but often modems will transmit at the same time in frequency. Another modem nearby in the neighborhood is actually trying to receive on that frequency, or very close, subcarrier frequency, very close to that frequency. And that causes interferences between modems. Co-channel interference, adjacent channel interference, and adjacent leakage interference. I'm not going to go into them all, but co-channel interference I'm going to explain to you guys. FDX relies strongly on echo cancellations. All these disturbances here are called echoes, and also the impedance mismatch echoes are also called echoes. Any kind of disturbance signal is called an echo in FDX. Why is that a problem if one modem is sending an upstream signal while a modem nearby is receiving a downstream signal on that same subcarrier? Because you got to keep in mind the relations. We're usually using dBs. dB is a logarithmic kind of scaling, which makes big numbers small. Right? So 60 dB is actually a big factor. It's comparable to, let's say, the transmission of a downstream or an upstream. As it comes out of the amplifier, let's say 105 dB microvolts. It's like 45 dB millivolts. It's comparable to this 20-meter wave here. Now it traverses the transmission line. Coax does attenuate quite a lot, much more than fiber. It traverses the transmission line until it gets received at the customer. And this 20-meter wave got attenuated so much that it's like this 2-centimeter ripple down here, a factor 1,000. 60 dB, 50, probably it's usually 50 dB, but I take 60 because it's a bit nicer to calculate. That's a factor 1,000 when you're expressing the power with the voltages that drive the power. If you take in the powers in watts, it's a factor 1 million. So, not much is left of your transmission. This is being received on a downstream while the modem in the next house is using that same subcarrier to send an upstream frequency. Some of that energy is going to bleed over into that transmission. It's going to be destroying this reception. Better to be explained on this picture here. Just keep in mind, same relation also holds when upstream transmission is done, then comes out of the modems, also big 20-meter wave, while a downstream here, this here, modem, 20-meter wave, upstream transmission on this tap here, while there's a modem on the tap on the same C line, the next tap, that is actually receiving on that same upstream. If it's the same subcarrier frequency, we talk about co-channel interference, because this tap here, the tap and the exit into the line, they are not filtered or anything. They're just decoupled like 20-something dB, which means 20 dB is 1%. 1% of the power of this upstream transmission, the 20-meter wave coming out here, is actually bleeding into this downstream reception here, and it's almost at the house. It's like 2 centimeters big in my example. Just 1% of the 20 centimeters bleeds over this. It's going to annihilate your downstream reception. This guy is not going to be getting his data. And that is a situation you need to avoid. So co-channel interference means it's the same subcarrier we're talking about. The same thing holds for adjacent channel interference. Then we're not considering the same subcarrier here at this modem. We're considering the subcarrier left and right to the one in question. Adjacent leakage means we're considering a group of subcarriers left and right. So it's basically a result of using directional couplers. So now directional isolation is perfect, and part of this upstream signal energy leaks into the downstream. You always have those problems with that FDX region. The further apart the taps are, the smaller the effect of the CCI or the ACI or the ALI. Why? Because your disturbance signal also is traversing your transmission line and gets attenuated. Yeah, good. Yeah, this is a good picture here down here. Upstream transmission, downstream reception, and then the CCI. And you see the CCI is probably bigger than your downstream reception, which means it's a negative SNR. Negative SNR is like really bad. More noise than signal. Echoes. Impedance mismatches. Every connector, every tap, every entry in an amplifier will squeeze the coax cable just a little bit and will shift it off its 75 ohm system impedance. Whenever you have that, part of the energy, part of the power that you're transmitting across this device will get reflected into the line. into the direction it came from, and overlay whatever is coming down the line at that point. So we've always had that in our Docsis systems and our coax systems, and we will always have that. Now we're getting even more problems because we have these additional disturbances. But reflections of a signal are dependent on the location of taps within the transmission line. Downstream echoes reach the fiber node, time delayed and attenuated. Echo levels are rising with frequency. You see this downstream transmission, it reflects off the tap 1, tap 2, tap 3, tap 4, tap 5, and anything that's in the line. And that takes a while. So you're going to get time-shifted echoes coming back. And that's going to be overlaying what you're sending. So you got to basically tell the transmitter, okay, there's an echo coming, reduce or up your level to counteract that. But if you know the times, and every time the system is being put, it's a repetitive process of determining the echo times it takes. There's always an echo learning process in this FDX. In the upstream, it looks a little bit different, because here, the modem, the location on the modem of the modem on the line is of ultimate importance. Look, here I have a modem on the second tap. He gets a reflection from the modem port. He gets a reflection from tap 2, from tap 1, and from the node. Much different down here. You got a modem on tap 5 in the line. You're going to get much more echoes down here. Much more work on the back of the line for FDX than at the front of the line. And that is these echoes and the times it takes until they reflect, that is something the CMTS needs to determine all the time, such that she can time when to counteract this echo. She knows what was sent, she knows how long it takes until it comes back, and then she, at that moment, will alter the transmission level, basically at the inverse of your reflection onto your signal. So FDX is all about canceling these echoes, right? And that's one of the problems when you're amplifying an FDX signal in this region. You will not get all echoes out, and you're amplifying your residual echo that you're having. And every amplification amplifies whatever noise is in the signal and adds its own noise, which means more noisy signals, which means less, not as high modulation orders, less bits on a symbol, less data throughput. That's why you see in the node functional block diagrams and the CMT cable modem functional block diagrams, I'm not going to go over this, but you see there's a big part here. All downstreams, all upstream signals, they all go into this self-interference and echo cancellation, gray square here, the functions that observe those signals and counteract those echoes. So the summary for the interferences, FDX poses a powerful system with thousands of little subcarriers, 25, 50 kilohertz wide, operating in both directions, maximizing our throughput. FDX is not quite as straightforward as extended spectrum. There's a whole bunch of trash in those signals that we need to calculate out. And that's why we're doing this now and not 20 years ago, because now we actually have chips that can calculate that fast. 20 years ago, they were not as powerful. Counteracting interference, how are we actually doing that? The CMTS needs to know. Well, who's disturbing whom? Like my modem here on my tap is doing upstream transmission. The neighbor's house gets disturbed, as I showed you, CCI. Well, those are values the CMTS needs to learn. That's why next to station maintenance, to probing, all these maintenance routines that the CMTS and the cable modems are going through, station maintenance or probing every 30 seconds, right? We need to add another one. It's called the sounding principle. Remember, transmission and reception, that big attenuation of a signal between transmitting and receiving, that was 60 dB, around about 50, 60 dB. Here's a house in Buenos Aires. Yeah. This principle that I'm explaining here, what's the time? That I'm explaining is sounding principle that the CMTS uses can be explained at this house. Let's see, you have Luciano Pavarotti down here, right? He's an opera star. He's dead these days. But let's say he lives down there, and his neighbors on these floors up here, they're all talking to their wives or their girlfriends, and they're listening, right? And Luciano down here goes and sings, "Don't cry for me, Argentina," something like that, right? Nice and loud. So what's happening? The guy right above him, he has one ceiling attenuation. He hears Luciano better than he hears his girlfriend, which is going to get him into trouble. So he's mad. He's got a bad SNR, negative SNR. More Luciano than his girlfriend. The guy on the first, second, third floor, he has got two ceilings of attenuation in there. Bigger distance. Well, he gets disturbed too, but he can hear his girlfriend. More girlfriend sound than Luciano, but still lots of noise. The further up you go, the better it gets. The guy upstairs cannot hear him sing down there. And that's a little bit what the CMTS does. The CMTS, on a regular basis, every 30 seconds, 1 minute, you know the timings in these systems. So the cable modem transmits special signals to each other and receive them from other cable modems as instructed by the CMTS. That's basically test code words are integrated into upstream bands for a cable modem on selected subcarriers. Other cable modems then measure the SNR on that signal. And the sounding then helps the CMTS to determine which cable modem will experience CCI or ACI-ALI disturbances from that transmission. CMTS will then go and determine, okay, well, if this guy here is transmitting, maybe his neighbor should not be receiving anything on that same frequency, but maybe few neighbors down, they can receive on that frequency, but maybe on a more robust modulation order, it gets disturbed. We need to protect the signal a bit, not as much data throughput, but definitely data throughput. Example of sounding here, periodic process, comparable to station maintenance, happens all the time. Here's Charlie. Charlie's singing, "Don't Cry for Me, Argentina." Boop. On the same tap, these guys get a negative SNR, a strong CCI, when they're on the same tap usually. These guys should not be transmitting or receiving anything on that same frequency or close to that frequency, subcarrier frequency, when Charlie is singing. My modem's always called Charlie. A tap further down, there's a little distance, cable distance between the two taps. That disturbance gets attenuated. So these guys over here, maybe they can actually receive their downstream when Charlie is singing, but on a very robust modulation order, as long as he's singing. These guys over here, even further away, well, they're cool. A little bit of disturbance, but we can handle that. Still a pretty high modulation order. I'm back here. These guys don't get disturbed much because there's a long path of transmission that attenuates that CCI. But that's the first modem there in the line. Oh yeah, that's Delta over here. He has had a bad night. Maybe he doesn't like how Charlie sings. You group these guys into interference groups. The CMTS will do this periodically. Who disturbs whom? How much? And all these guys will receive that test signal and will send back to the CMTS. Charlie disturbed me so and so much. I had an SNR of so and so many dB. And sends that back to the CMTS. Now she will go and say, well, I'll group you guys into interference groups. Interference groups means, or modems in an interference group, usually on one tap, means one guy is actually sending an upstream, all the other guys in that interference group should not be receiving anything on that frequency or close to that frequency. And so it goes on. If you're not in the same interference group, you're going to be in a transmission group. That means those modems can actually transmit and receive together under certain boundary conditions. Second example. Now it's not the first modem on the first tap. Let's say it's this one here. And these things, "Don't Cry for Me, Argentina." And all the modems that are also connected to tap 2, now they get that negative SNR. These guys cannot now receive anything while Charlie is transmitting. And the further away you are from that singer, the less disturbed you get. So every modem does that, and all the other guys are listening, sending the results to the CMTS. She keeps a table, who disturbs whom, under what circumstances, and with what kind of dB number. And according to that dB, she will associate a modulation order for that situation, as long as that situation prevails. So CMTS schedules transmissions from and to cable modems in the same interference group, such that they interfere minimally and adjusts the bit loading. So she's got a lot of work. That's why it's complicated. That's why you need lots of computational power. Okay, what's going on? Interference transmission groups, just said it. Cable modems interference groups with respect to each other determine how much they interfere. That's the positioning in the line. The higher the interference, the lower the SNR between them. SNR determines the data rate and corresponding bit loading for the subcarriers according to the noise scenario. Kind of like put down here in this table. I'm not going to go much over it, but you can see if it's tap 1 to tap 1, you always get negative SNRs, right? Or you get as much noise as you get signal level. That's the scenario where you cannot receive and send at the same time. All others, yes, disturbance can be counteracted with more robust modulation orders. Cable modems on the same tap achieve a low SNR. That's a given. The SNR between taps toward the end of an access line reduces fast. As I said, you remember the echoes at the end of the access line increase. The SNR between two taps stays about equal, no matter if you go in one direction or the other, upstream or downstream, because it's in the same frequency region. And that's a periodic process. It happens all the time, every 30 seconds probably. So that's why I call FDX Docsis on steroids. Engineers on steroids kind of look like this down there, right? So, complexity. So this full duplex Docsis is highly complex. Hardware designers, cable labs have been doing a lot of research here, lab trials. In the lab, it works wonderfully. But in real-world circumstances, there's test areas out there in the USA. Every network operator has one. And I think Comcast has achieved like 5 gigabits per second symmetrically under real-world conditions up to this point. So this takes a lot of pimping and a lot of research and a lot of trying. It's never really done in a live network apart from these test areas. Well, I already said that. Echo cancellation will be critical. How's the performance in the real world? We're trying to find out. We realize a lab scenario is a lot more easy than the real world. We have impaired drop cables in the United States. Squirrels are eating them up, and the Americans are firing at the squirrels. You know, guns in America, right? In North America, sometimes they don't hit the squirrel, they hit the line, and then you get a really big echo, right? So it's highly complex, but it's worth it, because this will prolong the lifetime of your coaxial plan for another 10 years. Problem is, you will need to train your techies and your engineers to be able to operate a system like that and to debug a system like that. All DOCSIS 4.0 starts with DAA and remote PHY. You do not run a DOCSIS 4.0 system without having DAA in place. They're building stones for DOCSIS 4.0 deployment. They eliminate, as I said earlier, analog optics, pushes digital fiber very close to our customer. That digital fiber is then not shared with 500 people. It's kind of shared in the end with like 50 to 100 people, meaning they all share those 10 gigabit Ethernet. Less people on a node gets more of that bandwidth. The upstream noise funneling that we have in our DOCSIS networks, you know, all noise in the network that's created going up the upstream will end up on our CMTS at one point. That's called noise funneling. If we're now actually taking digital links, noise funneling doesn't go over optical fiber. It's a coaxial phenomenon. The coax ends on the optical nodes, so we have lots of little noise funnels. We don't get the noise of the entire network. We get the noise of a C line or a bunch of C lines, trunk lines, on the optical node. There's a lot less noise, lots less noise funneling, and therefore higher modulation orders in the upstream possible. And the upstream RF modulation and demodulation then takes place in the optical node. It doesn't take place in the CMTS. Right? You don't have to traverse kilometers, you have to traverse a couple of 100 meters. So FDX and DAA is a good combination for multi-dwelling units, and when you have aerial networks, also for a big footprint-wide rollout. But if you don't have that, like in Germany, we don't. We have to do lots of construction. Digging, civil works, the system might not be working that well. But in America, we're going to see this flying at least with Comcast. Summary of DOCSIS 4.0. Actually, still have some time. Summary of DOCSIS 4.0. Well, that's what gets us our symmetrical 10 gigabits per second. That's the reason why we're doing it. Puts network operators then in a competitive position with their fiber to the home competitors. potentially complicated, extremely powerful, but we got the technology to deal with that complication. Docsis 4.0 comes with 2 different implementation options. Full duplex DOCSIS, complicated, but to 1.2 gigahertz. Extended spectrum DOCSIS, same stuff we've been doing all this time, just bigger chunks of spectrum for up and downstream. But there we got to go and exchange not only our actives or our passives to 1.08 gigahertz. DAA is required for DOCSIS 4.0 operation. Incremental deployment of technology is possible, even desirable. You can upgrade with extended spectrum and full duplex. You can upgrade where it's possible, where it's feasible. You don't have to say, well, Google is building fiber all over my network. Now I got to pull fiber, pick up billions of dollars at the bank, and just do what the competition does, be driven by the competition. No, this gives you the chance, the possibility to extend your data throughput wherever in your footprint you need it, where the customers have that desire, where the throughput is not enough. It gives you a much more granular way of dealing with your network. Plus, you are in charge, and you're not just reacting because the market pushes you to do it. There are real-world challenges out there. Hardware, verification, interoperability. We have not dealt with a 600 megahertz upstream up to this point. Up to this point, we've had a tenth of that. For example, we have not dealt with a 1.8 gigahertz downstream. We've had half of that. So there's going to be some learning in that. And for the operation of DOCSIS 4.0, we need DAA, and we also need proactive network maintenance systems, which is a way of monitoring where your network, of analyzing live data in your networks, monitoring it, pre-equalization coefficient analysis. You can actually say my network is going to fail. Over here, that tap's going to be bad in 6 weeks and 2 days. Gives you the chance to mitigate the problem before the customer actually realizes there is a problem. These systems have grown into network management systems where you can actually see what quality of operation you are delivering to your customers. Not only where is it going to fail, but how's the system doing. You can't really run DOCSIS 4.0 without a good PNM system. DOCSIS 4.0 is cool, prolongs the life of coax for at least another decade, puts us in a comfortable position, and we're going to see if this is going to be the last step of DOCSIS, of coax, or if we're going to make more than 10 years out of this. Maybe we started DOCSIS saying, well, we're like 25 years ago, we're going to have 5 to 10 years more coax. Now it's 25 years down the line. Let's see how long this can last. In the end, we owe our customers a throughput, a data throughput. And the customer doesn't care really, mostly, how he gets that. All right. And since we have a little bit more time, I think I have until 1:15, right? 5 minutes, just pictures. Case study in Germany. Why? DOCSIS 4.0 is coming with difficulties in Germany. We have underground networks. And I hold it with Pulp Fiction on that one. You know, you've seen that movie, right? Everybody has seen that at one point. They got the same stuff in Europe they got over here. Theirs is just a little bit different. Like when you go into a movie theater in Amsterdam, you can actually order a glass of beer, not a plastic cup, a glass of beer. That's the example they're bringing, right? Little differences, and same holds for broadband networks. In Germany, the cable TV of the modern world of the 70s and 80s here was 12 programs in good quality. Where I grew up by the North Sea coast in a village, we had 2.5 programs, 3 analog programs. They started at 4 in the afternoon, and they were done at 12 at night, analog over a Yagi. And in Germany, often we get the federal government, we Germans look to the federal government a lot to make a law about something, right? So the cable TV networks, just the distribution networks, when they were built, were the responsibility of the federal government, the Federal Postal Services, the guys who deliver the letters, and the guys who also operated the telephone networks in Germany. So any kind of signal transmission, of course, that's what the post office does, right? Okay. So, and that's what this down here is. And Germany is an important market in Europe. 50% of all European cable households are located in Germany. And until 2000, then that was just a distribution network for analog TV signals run by the German postal services. Then it was privatized. It was sold to investors. The blue parts were American investors in 2000. they upgraded the networks. My company was part of it. We redesigned about half of that, and we implemented half of that in 2001 to 2003. And the first thing that got scratched was the documentation department that the Federal Postal Services actually had. They had a big department that would draw in every kind of change into the documentation, German accuracy, wonderful accurate. But it got privatized, and then they said, okay, well, we don't need that. We're going to have our techies and engineers, once they're done with exchanging a tap or putting in a new line, upgrade the documentation. That's a problem these days, because this has been going on for about 20 years now. And today, the location of many direct buried passives are not exactly known. Well, because, well, it was kind of written down. Nobody ever, in those private companies, put it into the documentation. So now, if you want to unearth a tap, you have to look for it. That costs a lot of money. 25% of the passives can get exchanged if you have direct buried networks, because otherwise you have to do too much civil works. It costs 500 euros to do a meter by a meter hole into the ground to go 60 centimeters deep. Right? And if you have to bury too much, then your business case is going to explode. So upgrade in Germany meant 25% of the passives can be exchanged. So it means 75% 20 years ago were still old passives, 300 megahertz, 450 megahertz passives. And we still have some in there. These days, this whole thing is in one hand again, and it's called Vodafone. That's how that looks, underground networks here. Well, 60 centimeters deep, lots of old passives, and we have in-house amplifiers. I'll get to that in a second, right? So it's always this kind of picture you get. In America, it looks a little bit like they put it up yesterday and they want to tear it down tomorrow because it's all aerial, but they can access it all. And 80% of all costs and service of a network lie in civil construction. Well, that's problematic if you want to go extended spectrum, if you now want to go 1.8 gigahertz. If you have some old taps in there that are designed to 450, it's not going to fly. So problematic extended spectrum, especially if you want to go in those higher frequency regions. American upgrades are easier. Well, the most expensive thing is the bucket truck, and paying the guy there. He's driving along the line. He's exchanging all actives, all passives, much cleaner signals. Next thing, FDX. So extended spectrum is bad because there's old taps in there and we can't unearth them all. FDX also comes with a problem because if it's a government responsibility, taxpayer money that builds a network, you're going to make a Mercedes. Yes, but you're going to extend the range. If you have to deliver a certain signal level, minimum this, maximum this, the postal office delivered it on the bottom of that window because they only owned the network into the house, not like into the basement. Basically street and the entry into the basement, not the network in the house. That was somebody else's because not everything was under government control. We were not East Germany, we were West Germany, right? So the situation is that basically in-street network is in one hand, and then there's companies that own 4 million in-house networks, no in-street, which means signal gets delivered into a house, it gets amplified. There's this demarcation point here. That's just basically where the signal enters. You can measure it here, and then it needs to get amplified. What did we say about amplification with full duplex Docsis? Kind of bad, right? Makes the signals a little bit more noisy. So we're not going to get full duplex Docsis in its full capacity unless we exchange all these in-house amplifiers. So Docsis 4.0 is not really going to fly like in the United States or in an aerial network with respect to extended spectrum or with respect to full duplex Docsis. We can engineer a way around it, of course, but it's a business case kind of thing. Oops, what am I doing? It's a business case kind of thing. Basically, you got to go line by line, section by section of your network and say, is it more feasible to basically put in a fiber here because I have to exchange 5 taps anyway? Now I have the construction crew here, let's just dig fiber to the houses, or is it more feasible to use the coaxial lines in some part of the network? So, and Vodafone just announced they're going to be overbuilding their own network, 7 million households with fiber because of this. Just for kicks, natural adversaries of cable, that's just for joke now. In Europe, it's water. Seeps into your lines, seeps into your taps after a while, and then they don't work. In America, it's a squirrel. Did you know that? Area lines, squirrels eat lines, and they eat through metal. Their teeth always grow. Right? So a tap's going to look like this. I mean, that's where it puts its fangs in right there, right? That's through. That's very, very bad for your electromagnetic shielding here. Plus, it's going to rain in there. That's the little squirrel. Squirrel's job's never done. And plus, in America, you got the guys with the guns. Not everybody, but in rural areas, people might take a little pop shot at that squirrel. And they might not hit the squirrel, they might hit the line. You got a bullet in the line. That's a reflection. So, most common problems in the United States is squirrel chew and bullets in the line. No joke. I prefer my dog. He sleeps 18 hours a day, and he does his chewing in 6, including my shoes. I know, poor animal. So, the upgrade here, N+0 architecture is optimal, fiber deep. We're doing that. Large-scale Docsis 4.0 deployment in Germany, unrealistic. German networks are separated in street level and in-house level. That's the problem, always has been, especially in this connotation. In-street level is designed for distance. In-house signals always require an amplification. That makes N+0 problematic. Passive infrastructure is direct buried. Upgrade of passives requires civil construction. If that's too much, it's mucho dólares, costly. But in combination with DAA, you can actually use Docsis 4.0 for multi-dwelling units. You put that fiber in the basement, put the optical node into the basement, you use the existing coaxial in-house network for Docsis 4.0. That's actually a feasible option in that situation. The moral of the story is, yeah, it's a great technology, but it always depends on the boundary conditions of your network. Every upgrade is different for every network operator, depending on what kind of network he has, what kind of legacy, what kind of signals, what kind of customer base. Everybody needs to make their own business case on that. Cool. And with that, I wish you guys a very happy Football World Cup here. Argentina as one of my favorite teams here, right? I think these guys are going fast. Yep. Yep. As a German, I can say, German soccer team usually when in a tournament it goes against Argentina, that's usually like the most respected adversary. Everybody goes, oh, this is going to be really, really tough, right? Because these guys fight. Right on. Aloha, ladies and gentlemen. Thank you very much for your attention. It's great being here. Thank you. Right on. And I guess I spoke all my time, but do you have questions?
As usual.
Juanito has a question.
Well, two small questions. One is regarding full duplex Docsis.
Yeah.
As you said, it is clear to understand the best scenario is node +0.
Yes.
But when we have an intermediate amplifier, what happens with the full duplex band? Because amplifiers are one way. We can amplify forward, we can amplify reverse, and we can pass the full duplex band,
It takes special
but not amplify.
For the upgrade, extended spectrum, you will have to upgrade with amplifiers that actually can do that amplification of the extended spectrum. For full duplex Docsis, you will need to have special full duplex Docsis amplifiers that actually do that amplification in both directions in the FDX.
How do we detect the direction of that transmission? We can split the band in 3 areas. We can amplify forward. We can amplify return. But the two-way.
You use directional couplers for that. If you use an array of directional couplers, you can actually separate your up and down.
We transmit in one direction, and sometimes we.
One subcarrier, 1 second can be, or millisecond can be used for
with
downstream
directional
and
couplers.
for upstream.
With directional coupler, we select according to the direction.
Which is, I know directional couplers they're not perfect, and you get all that noise, right? That's the problem with directional couplers, and that's why this is a problematic region. But yes, you're putting it through an array of directional couplers, and you amplify, you separate the directions that way.
And also maybe stability problems.
Yes, that's
an oscillation risk.
That's one of those things that works well in the lab. And then when you get out in the field and you go, there's real-life problems, that's one of those things that is more prevalent once you're out in the field with unpredictable conditions. Yeah. So yes, in theory, this is great. Cable Labs came out with this a few years ago, and since then they're pimping it a lot longer than they pimped the 3.1. Sorry, improved the 3.1 or the 3.0 standard. Right? That wasn't straightforward, but it didn't take them about 3 years to get it operational in the field. Well, that's what Comcast, Charter, Cox in the United States are working on. They all put aside like a little test area where they actually implemented 4.0, and for the past 2-3 years, they've been analyzing how this works. We've been upgrading that system, analyzing it, see where are the problems, and then giving this back to Cable Labs to work on it. So it's an iterative process, and it takes a little longer than our previous upgrades because it's also a little bit more complicated.
If I understand, instead of using a duplex filter, amplifiers for Docsis, full duplex Docsis, use directional couplers. No,
Yes.
no duplex filters.
For that FTX region.
Just
for the FTX region, you remember?
use both.
Yes.
Duplex filters plus directional couplers.
Yes. Because, as I said, when I put the picture up, right, you had that upstream region, you had
Yes.
that little transition band there,
Yes.
the FTX region, transition band, downstream. You have a generic downstream, you can filter that out. That's why you got the transition band. The generic upstream, you can filter that out. The FTX region, you can sometimes, colloquially, I say, it's a region that you can basically borrow upstream from your downstream, or borrow downstream from your upstream. That's a flexible region that you can use as you need it. But don't necessarily always have to activate and run at 100%. But in that region, in that FTX region, you cannot use a filter because these signals are 25 or 50 kilohertz apart and they're overlapping. There's no guard bands in between them. They're OFDM, right? So if you wanted to filter that, you would have to have a very steep flank filter. And the steeper the flank of a filter, vertical is impossible by nature, but the steeper the flank, the higher the overshoot, the more expensive it becomes. Therefore, directional couplers. Not perfect, can't filter, lots of trash, but we use computational power to get rid of those disturbances. So yes, more noisy system, but more powerful chips to then mitigate the effects of that noise. So a little bit like Docsis 3.1, where we also said, yeah, well, we were using LDPC, therefore we were actually sending modulation orders that do get disturbed, but we rely on the LDPC to correct it. And the LDPC is also part of Docsis 4.0, right? So, but the principle still holds, right? So we're actually banking on this thing going noisy, and us having enough computational power to get rid of that noise in real time. So highly mathematical.
Okay.
Cool though.
And last question. Last question. Don't leave. Regarding DAA, the future, I guess, there are two options: remote PHY and remote MAC-PHY.
Yeah.
I guess that the future will point to remote MAC-PHY in order to allow low latency Docsis 2. Yes. Because we don't get low latency with remote PHY. We need remote MAC-PHY to reduce the latency, right?
Yes, that's true. Exactly. Remote MAC-PHY just means that, remote PHY means you're taking the physical work of the modulation into the node. MAC is the level where the management messages between the CMTS and the
media access control.
Media access control, basically the logistics of the transport is being arranged. If you can do that from the node as well and just keep an aggregation module in your NOC for signals going outside into the internet, that would be another banking factor, because now you basically have all important signals of your system just traversing between your modem and your optical node. That's just a few hundred meters and not 10 kilometers down to your NOC. So that's definitely going to be low latency too.
What are we getting now from the vendors? Remote PHY or remote MAC-PHY?
There's I know a remote MAC-PHY system. Hold on, is it a MAC-PHY system in Denmark? Not quite sure. At least they planned it as one. But if that one is not, I'm not quite sure. I don't know of any other really remote MAC-PHY system fully in operation. Remote PHY is easier, and it makes a lot more sense for us to say, well, we go remote MAC-PHY, what we always do. We go remote MAC-PHY, we do the easy step first, and then we work from there. So MAC-PHY is first step. Phi is first step. MAC-PHY is the second step. Yeah. So
vendors like to sell system and upgradings every 2 years.
Pretty much, yeah.
Yeah.
So, plus, we got to have something that we can implement in a couple of years, right? No, it's easier. Remote PHY is easier to implement.
Remote PHY is easier.
Therefore, we need it. We need a remote PHY system on Docsis 4.0, at least remote PHY. And MAC-PHY actually works with extended spectrum, so it's a little problem to have it work with FDX at this point.
Yes, next step is move to FDX.
Yeah, and that's it. So right now they're trying to make it work properly with FDX, the remote MAC-PHY with FDX. It works fine with extended spectrum.
Okay, thank you.
Right on. More questions? Shoot them. No? No more questions? Well, there you go. Hold on.
Ok. La consulta es, ¿cuál sería, y si es que lo hay, un incremento en el procesador del CCAP Core al utilizar Full Duplex Docsis? Nosotros vimos que al migrar de una tecnología legacy a Remote PHY tuvimos hasta incrementos del 20% en el procesador. ¿Esto también se llevaría al incorporar Full Duplex Docsis con Docsis 4.0?
Yes, it should be. It should be probably even be a little higher than the 20% because compared to the past upgrades, this is going to be a high computational power technology. So yes, I expect that it's going to be a little higher than 3.1, but not massively. But I don't have any exact numbers.
Gracias.
Yep. More? Shoot him. No? Okay, well, if there's no more questions, again, I thank you very much, ladies and gentlemen.
Le agradecemos al doctor Alex Adams por acompañarnos.